Good morning, everybody. Welcome back to lecture number 11. Today, we will talk about the previous example of the two MMFs. So what is the circuit? Draw the circuit. Yalla, class activity. Draw the magnetic circuit. Ask yourself, how many reactances do I have?
Two.
Why two?
One. Here, one.
Reluctance, if I have a change in cross-sectional area or change of material. Do I have change in cross-sectional area? It's 15 by 15 all the way. 15 by 15. Now, do I have change in material, air gap, etc.? No. So I have one reluctance. I can put it here. How many MMFs do I have? Two. What is the first MMF? It gives me flux in which direction؟ شوف الفرق اللي هذا اللي عليه إذا هو قدام apply it this way. إذا هو ورا الكور it will be this way. فهذا الفلux is in the direction of. So what is the MMF? Positive. Now here, okay? Go to this. Where is the flux? Current goes here. Right hand rule. So the plus is here. So what is the equivalent circuit? Do you see the polarity? So both MMFs, they are in the direction supporting
Each
other's flux. How many fluxes do I have?
One.
Only one flux. في تفرع زي السيركت ما في تفرع. Get it? Now, I'm not going to solve this problem. It's easy. If you read the question, he's giving you the currents. I1, I2. So what is F1? N1, I1. What is F2? N2, I2. Do a KVL. Voltage rise or voltage drop? Or F1. Voltage rise or voltage drop? Flux يدخل مع positive minus. Voltage rise or voltage drop? If you do the classical method, you will just reverse the direction, the thing. Equals 0. So what does he want? He wants me to get what is the flux? So flux is nothing but F1 plus F2 over equivalent reluctance. Or it's one reluctance. We are professionals. What is the reluctance? Calculators. Quiz 2 is going to be hard. If you don't use the calculators now, you're not going to practice. You have a calculator?
No.
In the quiz, you can borrow a calculator with minus 0.5. That's the deal. That's the price of the calculator. So what is the reluctance? L core over mu times cross-sectional area. What is a mu? 1,000 mu naught. Mu naught is a constant. What is LC? Now, two ways to do it. There is the smart way, which Anas Zahrani will do it. Where is Anas Zahrani? Please come. Are you okay to appear in the camera?
Yeah.
Come. Now, what is the mean length? Draw an arrow. Write down quickly.
هنا 7.5 زائد 50 زائد 7.5 هنا بعدين هنا بيكون ضغط.
Yeah, but you are smart, you know. Give me a shortcut. I don't have time. Quickly now.
15 50 بعدين هنا و50 15 و50 15 من هنا و50 تطلع 260.
Gotcha. MashaAllah. Smart. Okay? Well, I'm not smart. This is 7.5 15. 15 زائد 50. 65 ضرب 4. 260. Get it? That's another way. I'm not going to teach you how to do these things, okay? That's why they teach you in PYP. Sandu. machine. Now, I know the mean length, I know the cross-sectional area, it's 15 by 15. It's 15 by 15 y. لما ترسم هذه الليج flux عندك هنا داخل 15 و this one is 15. Flux going here. And it's uniform. ما في change in the dimension. So to solve this problem, the flux is Ni1 times Ni1 plus N2I2 will give you 425. The reluctance is 92,000. If you divide them, you will get the flux of 4.62 milliweber. Get it?
Okay.
Get it now? It's easy. Do you remember this problem? If you see this problem in homework 2, how should I draw the MMF? We're going to have here plus, y plus, because the flux is going up, right hand rule. We're going to have another MMF here,
Plus, yes.
and we're going to have, how many fluxes do I have here? 1, 2, 3. Because even though the right leg looks similar to the left leg, focus on the homework, even though the right U-shaped leg and the left U-shaped leg, they look the same, but if I apply different currents, they would carry this different flux. Because they would carry different flux, I should model them as two separate reluctances. One is here, one is here. Get it? Please don't walk over the camera. Why do you want to close? So you think it's better this way? Are you sure?
Yeah.
خلاص. We trust your opinion. Get it? ما كانت واضحة أكيد؟
Okay.
Good, thank you. And then I have a middle leg, صح? Because I have a middle leg, I have this circuit. How to solve it? It's homework. Maybe if you use mesh, you can use mesh and you can use node voltage analysis. You can use superposition. It's up to you, okay? So تقدر تمشمشها using mesh. That's the term the ME students came up with. When I taught EE 234 last semester, they came up with this term. You can use node voltage, but the problem with it is you need to get MMF. So don't use node voltage. You can use superposition. Okay? So you can calculate the flux due to this, the flux due to that, and you add them together. That's the professional way. So the professional way, superposition. You replace this with a short circuit, you do the calculation. You replace this with a short circuit, you do the calculation. Then you calculate the flux in the middle by summing them both. Okay? Get it?
دكتور إذا كان الام ام اف نفس بعض أقدر أفصل التو سيركت.
No, you cannot. No. Anyway, I gave you this. I'm not going to solve it because it might be a homework problem. Okay? Okay. Let's continue. What if I have a rotor in the middle? If I have a rotor in the middle, how many reluctances do I have?
2.
Not 2.
3
The first one is for the core,
air gap
2 for air gap 1, 3 for the rotor, 5 for
3
the other rotor, the other air gap. So total of 4. Or you can combine the two air gaps in one reluctance.
Yes.
That is correct. What is the cross-sectional area of the rotor when the flux is going?
Again?
What is the cross-sectional area of the rotor? What is the cross-sectional area of a cylindrical rotor? لما الفلكس
دائرة.
لا مو دائرة، دائرة لما الفلكس يجي هنا.
مستطيل.
مستطيل. What are the dimensions of هذا المستطيل? Clearly the problem does not give me the depth of the core. Okay? So the problem is looking at the core this way. This is the core. Yeah. This is. تخيل معي انك تلفها 90 درجة. شهري. Think of the rotor إنه ما له زوايا. ما له زوايا. Get it? That's why the cross sectional of it is same as the core. يعني that's the rotor. Think of it as the core زي كذا محتوي. Get it?
كلهم نفس الكروس سكشن.
Yes. هذه الإكزامبل كذا. فهمت؟ That's why he didn't give me the trick. So assume إنه هذا it has the same cross sectional area of 12 centimeters square, which is 12 over 10,000. Get it? Get it? Get it? Get it? So what is the cross sectional area of the rotor? It's same as the cross sectional area of the core. Maybe in the exam I tell you no. The cross-sectional area of the rotor is different. بسيطة. إذا كان designed this way وفيه زوايا طالعة برا. Is it possible?
Yes.
Yeah, it is possible. Why not? And then you need to do the dimensions, which is the diameter times the depth. Diameter times
the depth.
depth. Diameter times. You have to watch YouTube. Now it's getting harder. Okay? Now, this is the equivalent circuit. 4 reluctances. 4 reluctances, or you can have 3 reluctances if you combine the 2 air gaps. Reluctance 1 is for the core, which is 0.5 over 2000 mu naught times 12 centimeters square converted to meter, which is 166,000. Reluctance of the rotor is 0.05, the diameter of the rotor. What is the effective length of the rotor? حاطة لك 5 diameter. Get it?
Get it.
It is easy. Now, an air gap, he combined them, or you can repeat them twice. What is the effective length? 0.05 centimeter, which is 0.05 over 100 meter. And هذا 5 ملي وهذا 5 سم. Get it? Don't confuse the units, please. Once you do all R1, R2, R3, R4, you combine them. If you combine them, you'll get this number, 75,1000. 75,1000. Then you use the formula, F equal Ni. I know N from the problem. 200. What is I? 1 amp. So he's asking what is the flux density. So flux density is flux over area of the air gap. What is the cross-sectional area of the air gap? He's telling you cross-sectional area of the air gap, including the fringing, is 14 centimeters square. So it is the flux over 14 divided by 10K. 10K because to convert from centimeter to meter. Then I can get the flux density in the air gap. The final answer is 0.19. Solve these problems, ya shabab. If you do not solve them now, you will get stuck in the exam. Okay? Get it?
Okay.
So, yes.
دكتور الحين الراوتر ايش اللي حيثبته؟ ماجنتيك
الروتر.
الروتر اي
هو in reality
يكون ماجنتيك هو اللي حيثبته ولا؟
لا in reality the air gap is too small in reality in real life it's hooked with a shaft. في له shaft حديدة في النص.
هو الشفت هذا ما لها
هذا الشيب is only the steel ففي support structure. السبورت ستراكشر بلاستيك فيه له شافت يعلق. شافت في الميدل. once it starts spinning هو يرتفع شوية عن الشافت.
طب الشافت هذا ما راح يأثر في
الشافت aluminum. It has no magnetic features. Aluminum. Okay. We will talk about it when we talk about the motors. But for now, understand why do we have air gaps? For cooling and to allow rotors to move. Get it? Don't forget the transformer example, okay? Get it? So now when you buy a transformer, are you going to do these calculations?
Yes.
Okay. Did you finish your recipe? It's 129 hours
Yes.
or 128? So you're caught.
No, I am. Some.
You're missing 1 hour. Fix it next semester. Plan for an EE is 129. He is missing probably summer training محطوطة 0. Let's go.
I think summer training is 0.
Yeah, fix it. It's not now. After registration. خلاص. Now, do you remember the equation V equal mu times H? What is this equation? This equation is only valid for a linear region. So if I start increasing the H, how do I increase the H? What's the formula of H? It's Ni over L, something like that. Get it?
Okay.
So if I increase the current, I increase H. If I increase H, would I increase the magnetic flux density?
Yes. Yes.
Yes. If I have 1 million amp, would I get 1 million similar flux? No, life is not that easy. For some reason, the magnetic material has a saturation limit. You cannot exceed it, okay? Get it?
Okay.
Does it make sense to supply big H if I'm saturated?
No.
No, so we usually operate at the area called the knee. This is the optimal area because that's the maximum current I can add to get the maximum flux. Any incremental value of current is a waste of money. I don't care about power, money. Okay? So when you operate your motor or generator or transformer, make sure you are operating at the knee. Now, in motor, if you want to slow down the motor, you can reduce the current, slow down the flux, slow down the speed, can increase it. Think of it that way. So it is okay, as long as you're in the linear region, it is okay. We don't want to go into the saturation. Because if you go to the saturation, you might heat up, you might have irreversible damage. Okay? So, do not always assume mu is fixed. Because the slope, as you can see, changes. هنا يتغير وعند النية يتغير. It's not 100% linear. And this equation is only valid for what? Linear knee saturation. What region? Linear. Probably the knee too. Okay?
دكتور دنيا في لها two lines يعني two.
No, هذه اللاين هذه سلاب. شوف السلاب حقها والسلاب. السلاب حق هذه doesn't make sense. السلاب حق هذه is a big number. هنا بتقل الميو. I will show it in a second. هذا السلاب.
مو المفروض أنا أوصل للميو اللي فوق؟
Well, it depends. This is just symbolic. I will show you real life example.
أنا أقصد إنه أكون وصلت لبداية الساتوريشن وبعدين خلاص أوقف.
Yeah, that you can have your knee here or here or here or here. It's up to you. You're a designer engineer. Okay? Look at these curves. For the cast iron, this is the curve. It means for 500 amperes per meter, I have 0.3. For الكاست ستيل اللي هو وين راح اخويا؟ فولاذ. It has higher. For the same H, I get higher flux density.
Okay.
For silicon sheet steel, if I have the same amount of 500, it gives me 1.4 Hesman. So do you think manufacturers are stupid? No. They price this higher than that, higher than that. Get it?
على حسب الديزاين حقك والكوست.
For cost, design, application, availability. Maybe you don't have silicon sheet steel. So you need to ask, check what is the manufacturer. When you buy a transformer, don't forget to ask for the pH data. Otherwise, you cannot simulate it. You cannot do your math. And some of them, they lie in the data. As some of you lied in the lab. Some of you.
طب كيف أعرف هو والله ولا لا؟
You buy from a reputable manufacturer.
هذا الماتيريال حقت الكور ولا
Core. حديد الكور. الwindings نحاس. Copper. You can get it. There's many كهربائيين عندهم. But the core is not available everywhere. Okay? Maybe one day I'll ask you to open this for me. See what's inside. Maybe. I'm telling you the mu will change, right? Did I tell you that? Look at this curve. This curve always, as a professional engineer, you always look at the axis. And read what is here. Magnetization intensity H amperes per meter. Is this a linear scale or log scale?
Log.
It's log. I don't know how to read log scales, but I forgot. I don't know. But anyway, I think log scale. No, this is not log. This is power 10.
إيه طب هي كده اللوج.
No, not power 10. اللوج يكون
Decibel.
10 100 100,000. This is decibel. I don't know. Wallahi, I don't know. Anyway, it doesn't matter. Because for me, I don't care. For me, for 100H, what is my permeability? 6,000. For 500, what is my permeability? 2,000. For 50, what is my permeability? 5,500. So permeability changes itself until I go to the saturation. So you operate here at the knee, or maybe this is the knee. So you pick your permeability, you pick your design. Which mu you want to operate at. Okay? Remember the formula. What is the formula? B equal mu H. Always remind yourself, for linear. Maybe and the knee. Some of the knee, not all the knee. Okay? Okay? You can rewrite it and you can find mu R to be B over mu naught H. Exercise. Calculators. We have a class activity. I'm going to check my camera. It's working. Solve it. Who's not solving it? If you don't know, raise your hand. Now. I'm going to walk over. Greg, what happened? Explain. You want me to zoom?
Zoom.
Those who brought their iPads can view the form, can view the problem. I'm not going to read it. Basically, I want you to read the curve form.
دكتور
Don't tell me the answer. Show it to me by calculator.
لا بس سؤال الميو زيرو كيف اطلعها بالحاسبه؟
The mu zero is constant. 4 pi 10 to minus 7. Some people, I'm coming now. 1 second, please. I think a mu naught is what? Shift 7. Is it 17? Is it 17?
33
It's 33. Shift 7, 33.
جرب سوي شيفت 7
1.25 10 to minus 6. Shift 7, 33. Show me the calculation, please. Is it exactly the same? At 50. Is it 0.2 or a bit more? Because it's very critical at this region, okay? Roughly speaking. Got it. Did the other one?
First one. Should I say the number?
Hmm?
I got the first one.
You got it?
Yeah.
Oh, no one. It's an easy problem, yeah. Some of you are saying it's 0.2, some of you are... No, that's wrong. This is the second one? Yeah, that's correct. Some of you are saying, I think all of you got it. The point here is, for the same edge, for different edges, I get a new arc. Okay? Okay?
Yes.
So what was the first answer? Give me rough numbers.
3.1.
No, not 3 point.
360.
Give me 3,000.
3,660.
600. What's the other one?
1,200.
1,200. Okay? Leaking flux. Do you remember the print? Yes.
طلع فرق كبير عندي 3200 3600
So what was your H? What was your B from 50?
50 0.2
Okay?
أعلى شوي.
No, it's 0.23.
بيطلع الفرق هذا كبير
Yes? Yes. Because you're dividing by a small number. Get it?
Yes.
Do you remember the fringing?
Yes.
What was the fringing? Remember the picture. You have air gap. عندك الأقواس.
Yes, sir.
What was the implication on the problems? We get the effective air gap area to be bigger.
Yes.
So it's more reluctant. Unfortunately, it's not only that, we have also leakage somewhere else. Leakage somewhere else. Of course, the worst is at the air gap, but even around the coils, some of the flux would leak and come back. Some of the flux would leak and come back. Some of the flux would go here and leak. Maybe try to come back here. Unfortunately, we don't know how to calculate them. We need to run simulations, experiments, calculations. It's beyond the scope of this course. The only thing you need to out is that they are named because they leak out. They are bad. They are bad, okay? And sometimes we account for them. Sometimes we
Ignore it.
ignore them. Get it?
دكتور إذا عندي فرنجينج هل ممكن يكون ليكج أكثر؟
I don't know. It depends on the problem. But of course, the fringing is big. If you change the turns spacing more, would it change the leakage? Of course. إذا حطيتهم closer to each other, it will change. What we call the flux linkage. Now, you are familiar with an inductor, صح? And we told you the inductor stores a magnetic field. So is the coil that's wrapped around a core, does it resemble an inductor? Yes, because you're holding the magnetic field in the core. So it is similar as the inductor. The inductor, is it intrinsic feature of the device or it has to do with the supply, the inductance? زي المقاومة. It has to do with the geometry, material, etc. Clearly, we need to define a new quantity called flux linkage. Flux linkage. What is a flux linkage? N times the flux. It is number of turns times the flux. What's the unit of the flux? Weber. What's the unit of N? So turns times Weber. It's okay to have this unit. Now, an inductance by definition is the flux linkage over the current. This is from physics 102 or 305. I don't know which one you're taking. The one I didn't take, 305. Is it 305? Electricity and magnetism. Maybe you will see this equation. So it is Ni M flux over I. Math is hard. Substitute with stuff. Don't know how to do it. Ultimately, you get what? N square over R. What is R? Reluctance of what? The coil? Wrong. The core. Coil is copper. Doesn't have reluctance. So, modeling it as an inductor would be a problem. For example, this problem where he tells you cross-sectional area of the core and the air gap is the same. So did he ignore fringing or he didn't ignore? He ignored the fringing. So if you do the calculation, this is a typical problem, two reluctances, Ni over R equivalent. For I is 1, for 300 or 400 turns, he calculated the flux density to be 0.4 Tesla and the flux itself, which is this quantity, to be 0.6 times 10 to minus 3. Now, the only thing in this problem is he told you, okay, what is L? L is what? N times flux over I. Can you try L equal N square over reluctance? Where L equal N square over reluctance total. What is N square? 400 square. What is reluctance? I don't know, this number. 88 plus 530K. Is it the same? Is it 258 millihenry? $400 square over
258, yes.
Get it?
Yes.
So if I give you the magnetic circuit problem, you always expect the last part to ask about inductance. If you don't get this right, there is always hope to get it. N square over R or N times flux over I. Two formulas. Okay? Last thing we're going to talk about magnetic core losses. Camera. So what are the core losses? Core losses are heat.
قاعد تفلش
He doesn't فلش أخضر. الأمور طيبة. Okay. So hysteresis loss and eddy current هم الcore losses. ففي السيميليشن software sometimes they tell you core losses. هي عبارة عن الهستيريسيس زائد الإدي. Today we'll talk about only hysteresis. What is a hysteresis? If I have a core, circle or rectangle, and I send a current, a flux would go, صح? If I start from 0 at point A, if I increase the current, would the flux or flux density increase? Yeah. Maybe I increase here until I reach the knee. Okay, now I'm backing up, applying a negative current or reducing I, up until I reach I to be 0. Would I get the magnetic flux to be 0? No. There is residual flux. يجلس. أنت مغناطة بالكهرباء. It's not easy to demagnetize it. You need to apply a coercive force, negative current, to try to reverse it if you're lucky. Maybe you will not get lucky and go back to point E. Anyway, you're spinning in a loop called hysteresis loop. باختصار شديد, because if you apply a current on a core, in a coil with a core, you will magnetize the core. Even if you remove the current back to zero, the core would still be magnetized by a quantity called residual flux. You want to get rid of it, apply a coercive force until you reach a zero flux. Then you stop. If you keep going, more negative current. What does negative current mean?
The opposite direction.
Reverse direction or 180 degrees phase shift. Go here. Maybe you're lucky, come back. Maybe you're lucky, don't come back. Get it?
Okay.
Yes.
This hysteresis loop is بالعربي في المعجم يسمونها الفقدان التخلفي. This is an engineering Arabic dictionary. الإخوان السوريين they're doing very well at developing these. بيقول لك هي الطاقة التي تستنفذ في دورة مغناطيسية من جراء التخلفية المغناطيسية وهي تظهر في شكل حرارة. Get it? What is hysteresis? تخلفية. الاستبطاء. بعضنا يسمونها الاستبطاء. We'll just call it hysteresis. If I have a soft magnet or hard magnet has bigger hysteresis loop. Soft magnet has what?
No.
Smaller hysteresis loop. Lower hysteresis loss is good for machines, while higher is good for permanent magnet. We'll talk about it later. Last information is the equation to calculate it. It's a constant called, it is constant KH, which has to do with the volume and the hysteresis constant. Capital K or small k times the volume. Times the frequency of power, 1. So which one has more hysteresis? Saudiya or Bahrain? For the same transformer. Saudiya has more hysteresis, okay? So this is one of the advantages of the 50 Hz. You have lower hysteresis losses. But again, conservation of misery, we have bad things with the 50 Hz. Times the maximum flux with a constant n, you can have it 1.5 to 2.5 empirical formula. You're not required to memorize it, but if I give you a small problem, you can apply it, okay? Having said that, today we're done with the hysteresis. Next lecture we'll talk about eddy current. Eddy current in summary is تيار على شكل دوامة because of the frequency. And we'll talk about it next lecture. So next lecture we'll start with the fake quiz. What is a fake quiz?
What's this understand?
It means if you don't do well, I will call you on Teams. Why you did not do well in this course? It's not free, it's free of grade, but it's not free of responsibility. If you don't do it, I'll tell you why you did not do it. It's a quiz. Okay? So now you have to study the other sections quizzes, the other sections fake quizzes, and now you have a selection of all the exams. Okay? So how many quiz solutions do I have?
2.
Until now.
No, I put them in one file to make things easy.